Okay, so in this video, we're going to be going over the 2003 AP Calculus exam. So in this first question, we have a shaded region bounded by the graphs of y equals square root of x. So let me label that. This top one is y is equal to square root of x. And then we have y is equal to e to the negative 3x. E to the negative 3x. Okay, now let's see what's happening. And the vertical line x equals 1. Okay? So first we need to find the area of R. So a good first step when we're dealing with these kind of problems is to find the coordinates of this intersection point, especially the x-coordinate. So to find the x-coordinate, we're going to set the two functions equal to each other and then plug them in the calculator and see what happens. So we have one function, square root of x, and we have the other function, e to the negative 3x, and if we set these equal to each other, that's going to give us the x-coordinate of this point, right? So if we put this in our graphing calculator, where this is our y1 and this is our y2, and then we set these equal to each other and we find that x-coordinate, that's going to give us x being approximately equal to 0.239. And to make the answer as accurate as possible, I'm going to store this in a variable a. You can do this in your calculator, and whenever you need to use this number, this x-intersection point, this point A, I'll just use this variable a so that it'll make the answer exact by not needing to round. Okay, so now that we found this intersection point A, what we can do is first we need to identify the top curve and the bottom curve, right, of this area R. So this is the top curve for R, and this is the bottom curve for R. Let's label that. So let's say top is going to be, what is this one again? This is y equals square root of x, right? So the top is y equals square root of x, and then bottom is this one, that is y is equal to e to the negative 3x. Okay, and then the next question is, what is the bounds of integration? What is the x-coordinate of this left point, and what is the x-coordinate of this right point? So it's clear that the x-coordinate of this left point is a, as we found earlier, and the x-coordinate of the right point is 1. So what that means is when we're going to set up our integral here in a second, we're going to be going from a to 1, because that's the region that we want to find the area of. So let's see, we'll go from a to 1, and then what are we doing? So the formula here, when we're finding the area of this region, is it's going to be the top curve minus the bottom curve. That's just the general formula. So the top curve is square root of x, put that here, minus the bottom curve is e to the negative 3x, I'll put that there as well, e to the negative 3x, and then dx. So when this goes in our calculator, we can just put this in, we don't need to evaluate this manually. We're going to get approximately 0.443. That's the area of R. So you get 1 point here for setting up the integrand here, and another point for the correct answer. Now let's look at part B. Alright, part B. So now what we're asked to do is we're asked to find the volume of the solid generated when R is revolved around the horizontal line y equals 1. So let's see, what is this line y equals 1? Let's sketch that real quick on here. So y equals 1 is this horizontal line, so it'll look something like that, right? And then the first thing we want to notice is that there are two distances involved here. The first distance is this distance from the top curve, or from our horizontal line to the top curve, and the second distance is from the horizontal line to the bottom curve, like that. So a good first step here is to write the equation for both of these distances. Okay, so I'm going to call this small distance here, I'm going to call this little r. I'm going to call this big distance big R. So now this entire distance, this whole line from this horizontal line all the way to the x-axis, it's pretty clear that that height is 1, right? And then this section here from the graph to the x-axis, that distance is the square root of x, because that's the height of this function at any x value. That's the y value. So this height is square root of x. And since the total distance is 1, and this distance is square root of x, that means our remainder distance r is 1 minus square root of x. So we'll say that r is equal to 1 minus the square root of x. And then similarly, we can say that this whole distance here is 1, and then this small height here from the x-axis to the bottom curve, that's the y value, which is e to the negative 3x. That's kind of like the height, right? What, e to the negative 3x. So since the total distance is 1, and since this distance is e to the negative 3x, we can conclude that this big R is 1 minus e to the negative 3x. And then now we're just going to set up another integral using the formula. So remember, the formula for finding a volume when r is revolved around some distance is, it's going to be a pi. Let me do it in a different color actually. Let's do this blue. That looks nice. So we'll have a pi, and the integral from the first point to the second point. We don't know what those are just yet. And then it's going to be big R squared minus little r squared dx, right? So now what are all these numbers? Well, we know that a and b are the bounds of integration, right? That's the x coordinate of where we're starting, the x coordinate of where we're ending. And just like last time, we're starting at a, we're ending at 1. So we're going to be going from a to 1. So when we rewrite this integral for real, we'll have pi integral from a to 1. Remember, a is the x coordinate. That's whatever that was. It's like 0.4 something. So we're going from a to 1. And then big R is 1 minus e to the negative 3x. So we'll have 1 minus e to the negative 3x squared minus little r squared. That's 1 minus square root of x. So we'll have 1 minus square root of x squared dx. And then when you take this whole thing, plug it in the calculator, you'll get an output of 0.453 pi. Okay, that's your answer. You'll get 3 points here, 2 for the integrand, 1 for the answer. Now let's move on to the final part in this question. Alright, so in part C, we have a region R, and the region R is the base of a solid. So for this solid, each cross-section is a rectangle whose height is 5 times the length of its base. Okay, what does this mean? Well, let's try to draw a picture here. So it's going to be hard to kind of see in 3D, but we'll try. So we have a rectangle, and its base is a length R. So we'll have, that's the base. And the height is going to be 5 times that. So let's see if I can. The height is going to be 5 times that. And that's true for any point here. So if we have this, it has a height 5r as well. That's height is 5r. It's kind of a bad drawing, but you can see it's just an infinite number of rectangles whose height is 5 times their base. Right? So we need to find the area of this, or the volume of the shape generated when there's an infinite number of these rectangles. So the way we started this problem is first we need to find the area of one of these rectangles, right? So we know that the area of a rectangle, so the area of any rectangle, just the general formula is its base times its height, right? So they give us that the base is this distance, and the height is 5 times that distance, right? So the question is now, what is this distance here? And the way we can figure that out is, it is the difference between this top curve and the bottom curve. It's like the distance between square root of x and e to the negative 3x, right? So that means that the distance is this, the top curve, minus the bottom curve. It's like the difference in the distances. So the base b equals the top curve minus the bottom curve, e to the negative 3x. If that doesn't make sense, think about it as this whole distance is square root of x from square root of x to the bottom, and this small distance here is e to the negative 3x. So that means this remainder distance, that's this height, that's the height of r, I guess the base of r, that's going to be the difference between square root of x and e to the negative 3x. So now that we have our base, we know that our height is 5 times the base. So it's 5 times this stuff here. 5 times square root of x minus e to the negative 3x, like that. And then so the area is base times height. So the area will be, what happens when you multiply these two together, which will get you 5 times square root of x minus e to the negative 3x squared. Okay? So that's the area of one of these rectangles for a given x value. But we want to add up all of the rectangles from a until 1. So what we're going to do is we're going to integrate the area from this starting point A all the way until we get this ending point 1. And it's going to add up all of the individual areas of the rectangles in the region R. So we'll integrate from A to 1, and we're going to integrate this area function. So 5 times that 3x squared dx goes straight in your calculator, and we get 1.554 as our answer. So you get 2 points for the integrand and 1 point for the answer. That's question 1. Moving on. Okay, question 2, for a particle motion problem. These problems kind of take a really long time to explain, especially this one. So if I'm going a little bit faster in my explanation, that's why. I want to get this video finished in a timely fashion and not have it take 90 minutes. So we have a particle moving along the x-axis, and we have its velocity function. A good step, I think, to take is to go through all the parts of the problem and underline the key words and just have it in the back of your brain and just, think about different strategies that could be related to the words. So we have acceleration here, we have speed, we have changing direction, total distance traveled, more distance. Okay, so now that we went and underlined all the key words, that's going to help us a lot. So we need to first find the acceleration at time t equals 2. Okay? So now that we underlined the keyword acceleration, we should already be thinking in our mind, acceleration, that's the derivative of velocity. So if we want to find the acceleration at time t equals 2, a of 2, that's going to be the same as the derivative of the velocity at 2, v prime of 2, right? So what is this going to be? Well, you can find v prime of 2 by taking the velocity function, plugging it into your calculator, and telling it to give you the output at time t equals 2. Okay, so if you do this, put this in the calculator, you're going to get an output of 1.588. Okay? And it's important to show this intermediate step v prime of 2, even if you don't know for sure if it's going to get you any points, but it's nice for your grader to be able to see your work, for them to be able to, help you as much as they can and understand your thought process throughout the problem. Okay, so the second part of this question is the speed increasing at t equals 2, why or why not? So if we were thinking about speed, the first thing that should come to mind is what the sign of the velocity and the acceleration. So when we're dealing with speed, if the velocity and the acceleration have the same sign at a certain t value, then it's speeding up. The speed is increasing. If the acceleration and the velocity have opposite signs at that t value, then the particle is slowing down. So at t equals 2, if we want to find if the speed is increasing or decreasing, we know a of 2 is positive. We need to check v of 2. Okay, is v of 2 positive or negative? So I can plug in 2 into here, and I'm going to get negative 3 times sine of t squared over 2 is sine of 2. And while sine of 2, this is a positive number since it's in the second quadrant in the unit circle. So if we have a negative number times a positive number, it's going to give us a negative number. So the velocity at 2 is negative, the acceleration at 2 is positive. They have opposite signs. That implies that the particle is slowing down. So when we're given an explanation, we're not going to talk about a of 2, we're just going to talk about v prime of 2, because when we're going to explain, it's just a good habit to get into to refer to only the functions they give you. So they gave us velocity, so we're not going to refer to acceleration at all, we're just going to talk about v and v prime. So our answer is going to be something like, since v of 2 and v prime of 2 have opposite signs at t equals 2, the speed is decreasing. Okay? Now let's look at the next. Points. Forgot. So you get 1 point for the right answer for a of 2, and 1 point for explanation that the velocity or the speed is decreasing since v of 2 and v prime of 2 have opposite signs. Alright, part B. Find all times t from 0 to 3 where the particle changes direction. Justify your answer. So changes direction. That's another key word when you see part B. So when you think of changing direction, the first thing that should come to your mind when you see those words is the velocity switches sign. So it switches from positive to negative or negative to positive. And the way we're going to figure that out is we're first going to set the velocity equal to 0 to find all the points where it equals 0. Because when it switches sign, it's going to have to go from a number above 0 to a number below 0 or vice versa. So it's going to pass through 0. So if we set the velocity equal to 0, we'll get all the candidate values of t. Okay, so we'll have negative of t plus 1 times sine of t squared over 2 equals 0. And then, so let's split this up into two parts. We'll have negative of t plus 1 equals 0. And that's going to get us t equals negative 1. But since we're only dealing with t values between 0 and 3, that's not going to be very useful for us. So we'll just eliminate that and say that this negative t plus 1, that gives us no solutions. So now this next part, sine of t squared over 2. So we'll say sine t squared over 2 equals 0. So what are all the values of sine of what could equal 0? Well, if we just list different things that we know sine of 0 equals 0. We know sine of pi equals 0. And we know that sine of 2 pi equals 0. There could be more. There are definitely more. But when we go that far, we're probably going to be exceeding the maximum t value of 3, right? So let's just stop with this for now. So we know that t squared over 2 could be equal to 0. We know that t squared over 2 could be equal to pi. And we know that t squared over 2 could be equal to 2 pi, right? Because then that would make sine of that 0. Let's see. This would imply that t equals 0, right? If t squared over 2 is equal to 0, t equals 0, and that does not work. Okay? This would imply that t is equal to the square root of 2 pi, and that is definitely a number that is between 0 and 3, so this is valid. This is good. And then this would imply that t is the square root of 4 pi, which is actually greater than 3, so that would not be valid. What does that mean? Well, it means that this is the only valid t value that satisfies the conditions between 0 and 3, where the particle changes direction. So, actually, wait, we don't know that for sure. All we know is that this is the only valid candidate point, right? To test whether it's actually the only point where the particle changes direction, we can set up a sign chart like so. We'll set up a sign chart, and we'll have this t value here, and we're going from 0 to 3. And then let's see. So we need to check the sign of the velocity. So if I plug in a number into the velocity function between 0 and the square root of 2 pi, if that number comes out to be positive, then everything here is going to be positive, right? So if I choose a random number, whatever I want, between 0 and the square root of 2 pi, you'll find that the velocity will be negative there. If you take it and plug it into here, you'll always get a negative number. Likewise, if you take a number and you plug it into here, you're always going to get a positive number. So what does that imply? Well, since the sign switches from the velocity switches from negative to positive at t equals square root of 2 pi, that means that the velocity switches sign, so the particle changes direction at this time as well. For our explanation, we'd say that, because the one explanation as to why this why the particle changes direction there. So we'd say that since the velocity switches sign at t equals square root of 2 pi, therefore the particle changes direction there as well. So we would get 1 point for identifying that t equals square root of 2 pi is the only candidate option. And then we'd get another point for saying that that's the only time where it switches direction, because that is the only time where the velocity switches sign. Part C. Find the total distance traveled by the particle from time t equals 0 to t equals 3. Keyword here, total distance. So when you think of total distance, when you think of distance in general, distance is the absolute the integral of the absolute value of velocity. This is what should come to your mind. It's the integral of speed, and speed is the absolute value of velocity. So since they want the distance between 0 and 3, we can just take this integral between 0 and 3. So the integral from 0 to 3 of the absolute value of the velocity function. I'm not going to write the whole thing out. I'll just say v of t. Right? dt. And then if you plug this in your calculator, you will get to do 4.334 as your answer. As for points, you should always love when you see these kind of questions because they're really, really short, but they just have so many points in them. You need 1 point for the bounds of 0 and 3, 1 point for including this absolute value of the velocity, and then another point for the answer. This must have taken you, 30 seconds of work? That's 3 points right there. That's pretty good. Okay, so after that easy question, part C, we have this actually quite difficult part D. So during the time interval from 0 to 3, what is the greatest distance between the particle and the origin? So I think the best way to approach this problem is to draw not exactly a graph, but like a diagram of the particle's motion. So let's draw like a little line, the x-axis. And then so we know that at time t equals 0, the particle is in position x equals 1, right? So we'll label that here, 1. That's its starting position. And I'll label this as 0. And then, let's see. To solve this problem effectively, we need to know that, we need to remember our velocity diagram from part B, where we do the square root of 2 pi, we have 0, and we have 3, and we have it a negative here and a positive here, right? This is for v of t. This means the velocity between 0 and square root of 2 pi was negative, and then from square root of 2 pi to 3 it was positive. Okay, so what that means is at first the velocity began moving this way, and then at square root of 2 pi it switched and it began moving that way again. Alright, and now the question is, when it started moving left, did it cross the 0 point or did it stay on this side? And the way we're going to figure that out is by taking the integral of the absolute value of velocity from 0 to square root of 2 pi. So that's going to get us the total distance that the particle traveled. If the distance is greater than 1, that means it crossed the x-axis. It crossed x equals 0. If it's less than 1, it did not. So if we evaluate this integral, it comes out to be 3.265. And then, since this number is greater than 1, that means the particle went like here. It went total distance of 3.265, right? This is at negative, 2.265, and this is at time t equals square root of 2 pi. Okay, and then now the particle moves this way again, right? Because after square root of 2 pi, it began moving to the right. And now we need to think when it ended its motion, right? When the particle stopped moving at time t equals 3, where was it? Because remember, we're trying to find out where the greatest distance is between the particle and the origin. So one option is it could be right here, because this is like the greatest distance. Or maybe the particle went really, 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 really far over here, and this is the greatest distance, right? We don't know which one it was, so we're going to have to figure that out. The way we're going to figure that out is we're going to say, okay, how far did the particle move between square root of 2 pi and 3? Well, the distance that particle moved between square root of 2 pi and 3, we can figure that out as the integral from square root of 2 pi to 3 of the absolute value of velocity. I don't really need the absolute value because it was positive, but whatever. And we get 1.1. What does that mean? Well, it means that the particle moved 1.1. And since the square root of 2, so this distance here is 2.265, right? We label that, this is 2.265, and the integral is just 1.1. That means we only moved like this much. This is the particle's position. Sorry, this is the particle's position at time t equals 3. Okay, so we started here at t equals 0. We went all the way here at t equals square root of 2 pi. We went back at t equals 3. So it's clear that since this is the part where it changed direction, and t equals 3, this is not farther away from the origin than this is. It's pretty clear from our diagram here that this is the time where the particle is farthest from the origin. Okay, and what is that distance, they ask? Well, that's going to be the distance from here to here. And like we already said, that's 2.265, right? It's 3.265 minus 1 is 2.265. So our answer here is going to be I'll do it down here maybe. So the answer is going to be 2.265. Did they ask for anything else? Show the work related to your answer. We don't need to justify. We circled our answer. We showed our work. We're done with this question. Let's move on to the next one. Of course, I forgot to tell you the points again, like I always do. 1 point for integrating velocity and getting either positive this or negative this, depending on whether you chose to put the absolute value here. So you still get points if you got negative 3.265, and then you get another point for the final correct answer. Notice that they say distance, so you want this number to be positive. Okay. Now let's actually move on to the next question. Alright, so question 3, we are asked about the rate of fuel consumption of an airplane flight given by the function r of t. We also have the graph of r of t here, and we have the table with a bunch of data points for r of t. So in part A of this question, we need to use data from the table to find an approximation for r prime of 45, and we have to include units of measure. Alright, so what we can do is to find an approximation for r prime of 45. So r prime of 45, that's the derivative of r at 45, right? So the derivative is the instantaneous slope. So we want to approximate the instantaneous slope at 45. So 45 is like maybe right there on our graph. So the instantaneous slope would look something like something like this maybe, right? I'd say it's a good instantaneous slope. So we don't actually have a function that we can differentiate to find the exact value of r prime of 45. So the closest that we can do is we can take 2 points that are close to 45 and say, I'll find the slope between those 2 points, and I'll say that's pretty close to the slope of 45 and call it good. So what I can do is I can take this point, 40, right? And I know what r of 40 is. And I can take this point here, 50. I know what r of 50 is. And I can say, alright, I'll find the slope between 40 and 50, and I'll say, well, that's pretty close to r prime of 45, right? So the way we're going to do that is we'll take r of 50 minus r of 40 over 50 minus 40. What is r of 50 and r of 40? Well, we just have to look in the table. That's 55 minus 40 over 10, which is 1.5. And then for units, since we're dealing with a slope, the units are going to be the units for the y-axis divided by the units for the x-axis. So what's the units for the rate of fuel consumption? Well, looking at the table here, looks like for r of t, the units are gallons per minute, and for the x-axis, the units are minutes for time. So since we're dealing with the units for the y-axis divided by the units for the x-axis, that's going to be gallons per minute divided by minute. So gallons per minute or a nicer way to put that is gallons per minute squared. Okay, that's our answer. So you get 1 point for correctly writing an equation for slope with two points that are close to 45, and then another point for the correct answer. So you don't exactly, I guess you don't have to choose 40 and 50. It does make the most sense, but I guess you could choose different points and you might get a slightly different answer, but you'll still get credit as long as you had the right idea. Alright, so part B, we need to figure out R prime of 45, given that the rate of fuel consumption is increasing fastest at t equals 45. So this first sentence here, the rate of fuel consumption is increasing fastest at t equals 45, that means nothing to us, right? You can't just look at that and instantly tell what that means. So let's try to convert that into an equation using variables and numbers to try to get a better grasp of what it is. So let's start from the beginning. The rate of fuel consumption. What is the rate of fuel consumption? Well, looking at our graph here, it seems that the rate of fuel consumption is the same thing as R of t. So the rate of fuel consumption, that is R of t. Right? And then it says it's increasing. So when you're dealing with increasing or decreasing, we're dealing with R prime of t now, right? We're dealing with R of t anymore. We're dealing with increasing, we're dealing with R prime of t. We're dealing with the derivative. And then it's increasing fastest. So it's increasing fastest, it's increasing at the highest value, so its derivative is at a maximum. Since it's increasing, which means R prime, and fastest, which means maximum. So R prime of t is at its maximum at t is equal to 45. So now we've taken this sentence and converted it into something that's a lot more understandable, right? Using words that we're familiar with and we know what they mean. So if R prime of t is at a maximum, what does that mean about R double prime of t? Well, remember that if a function is at its maximum, its derivative is 0 at that point. So since R of t is maximum, the derivative of R of t, which is R double prime of t, is equal to 0. Okay? So since R prime of t has a maximum at t equals 45, at t equals 45, R double prime of t is 0. So R double prime of 45 equals 0. Okay, and they also want us to explain our reasoning. We can just talk about what we just said. Well, R double prime is 0 at t equals 45, or R double prime of 45 is 0, because R prime of t has a maximum at t equals 45. So 1 point for your answer and 1 point for your explanation there as well. Okay, so part C, we need to approximate the value of the integral from 0 to 90 of R of t dt using the left Riemann sum with 5 subintervals indicated by the data in the table. Is this numerical approximation less than the value of the actual integral, and why? Alright, so let's see. So when we're dealing with a left Riemann sum, the formula for a left Riemann sum is as follows. It's going to be base 0, I guess, times height 0, plus base 1, height 1, plus base 2, height 2, and so on. Okay? So what are the values of b0, h0, whatever? Well, let's see. If we're doing with b0, that's going to be the first base of our approximation, right? So since we're going from 0 to 90 with the 5 subintervals, the first subintervals can go from 0 to 30. So it's going to be this distance. It's not a good drawing of it. It's going to go from 0 to 30. The second one is going to go from 30 to 40. The next one is going to go from 40 to 50. The next one is going to go from 50 to 70. And the next one from there is going to go from 70 to 90. So that just came from 0 to 30, 30 to 40, so yada. So those are the values for the bases, right? B0, B1, B2, and so on. Now what about the heights? Well, that's where we have to look at whether it's a left Riemann sum or a right Riemann sum. So for the first base, we're dealing with these 2 points, right? 0 and 30. So if we're dealing with the left Riemann sum, the height is going to be the left height, this one. If we were dealing with the right Riemann sum, then the height would be the right point. So dealing with the left Riemann sum, it's going to be this height here. So that's going to be our height 0. 20 is going to be our height 0. And then for the second set, for the second base, we're going to be dealing with 30 and 40, right? Well, this is the left base, so it's going to be our height 1. And you can go on and look at the next set, where we're dealing with 40 and 50. Well, guess what? This is the left height, so it's going to be your height 2. So now it's enough talking. Let's plug in some numbers, right? So base 0 is going to be from 0 to 30, so it's going to be 30. Times height 0 is 20. Plus the first base, so from 30 to 40, that's 10. And then the height is 30. Plus, and then now we're going from 40 to 50, so it's another 10. That's this point 40. And I can just keep going on and on and on. 20, 55, 20, 65. And then if you evaluated this whole thing out, it'd come out to be 3,700. Okay? And then now let's think about, is this numerical approximation less than the value or greater than the value? So this is an approximation. This isn't the exact value, because we're leaving out some stuff. This is just an approximation for the area under this curve from 0 to 90. That's what we're really doing with our Riemann sum, right? We're taking this value from 0 to 90, we're approximating this area. Okay? So, now to think about whether the function is an overestimate or an underestimate, sorry, this approximation is an overestimate or underestimate, we have to think about the function, whether the function is increasing or decreasing. So if you have a function that's increasing, like this, so if you have a function that's increasing like this, and you're using your left Riemann sums, the approximation you were making would look something like this. And so on, right? So notice how we're leaving out some extra space in between, right? And that's causing this to be an underestimate. The actual value of the integral is going to be greater than what our estimate says, because the function is leaving out some extra little gaps here between each rectangle. So that's if the function is increasing, then we have that our Riemann sum, our left Riemann sum, is a underestimate, right? But now let's look at what happens if the function is decreasing. Right? If we're using our left Riemann sum, that is not a function that's decreasing. Let's try again. There we go, that's a function that's decreasing. So now if we were to do another left Riemann sum for this, we'd have something like this. Right? Now notice how here we have these extra areas, drawn in blue, that are overdoing. We have everything that's in the function plus this extra bit. So if we just rely on the left Riemann sum here, it's going to be an overestimate because we're also including this extra stuff that isn't in the actual integral. So notice that if the function is decreasing, the left Riemann sum overestimates the area, and if the function is increasing, the left Riemann sum underestimates the area. Now in our case, we have a function that is increasing, and that's even given to us that r of t is a strictly increasing function. So what that means is that we're going to fall under this category. The function is increasing. So that means that our left Riemann sum is underestimating the area. So we'd say that, well, okay, the function is increasing, so the left Riemann sum is underestimating the area. That's what you'd put for your explanation. Okay? So 1 point for the correct answer, 1 point for the explanation. Okay, so finally for part D, for 0 to 90, explain the meaning of the integral from 0 to b of r of t, and the integral, or 1 over b times integral from 0 to b of r of t. Okay, so let's take a look at what r of t is. R of t is the rate of fuel consumption, right? That's what it tells us in the graph. Rate of fuel consumption, RFT. So, since RFT is the rate of fuel consumption, the integral of RFT dt therefore is the amount of fuel. Consumed. And if that doesn't make intuitive sense, take a look at the units. When we're dealing with an integral, we want to find the area under the curve here, right? The units for that integral are going to be the units for the y-axis times the units for the x-axis. So since the units for the y-axis are gallons per minute, and the units for the x-axis are minutes, the units for the integral is going to be gallons per minute times minutes, which gives us gallons. So the integral of RFT is gallons, right? The units for that are going to be gallons, and what that means is the integral gives us the amount of gallons of fuel consumed at a certain time. Okay, so that's what the integral from 0 to b of RFT is. If we're having a certain time t, or a certain time b, that's between 0 and 90, the integral from 0 to b is going to give us the total amount of fuel consumed at any time b. Okay, so I guess another way you could say that is the amount of fuel in the first b minutes. And then, when we're giving our explanation in our answer, they want us to include units of measure. I butchered that, hold on. Include units of measure. So we can say, well, the integral from 0 to b of RFT is fuel consumed in gallons in the first b minutes. Okay, and then this 1 over b thing, that's something you should just know that as soon as you see a 1 over b. Whenever you see like a 1 over something times an integral, the thing that should instantly come to your mind is average value. Because there's usually no other reason they'll give you 1 over something times an integral. When you see that, you should immediately think, okay, that's average value. That's the average value of fuel. That's average value of RFT, right? Because, or is this? Yeah, so the 1 over b times the integral from 0 to b of r of t dt. Remember this integral here, this is the total amount of fuel consumed. This is the 1 over the time. So this gives us the average value of r of t. What is r of t again? R of t is the rate of fuel consumption. So the average value of the rate of fuel consumption is this. This is the average value of r of t. So the average value of, what is r of t? R of t is the rate of fuel consumption, right? So our average value of rate of fuel consumption. And then for units, if we're dealing with units, well, the average value of r of t is still going to be the same units of r of t. It's still just like another data point in r of t, right? So the average value is going to have the same units that r of t does, which is gallons per minute. So this is in gallons per minute. And this is what you say for your explanation, basically. 1 over b times the integral from 0 to b is the average value of the rate of fuel consumption in gallons per minute. And if you want, you can say it's in the first b minutes, because that's why there's a mention of b. Since they're giving us this extra variable b, you might want to mention b in both your answers, just to make sure you're dealing with the information they give you. Okay, so for points, this is a 3-point question. 1 point for correctly answering the meaning of this first integral. The second point for correctly mentioning the meaning of the second integral. And then 1 point for including correct units in both places. For both the first and the second, if you did both, you'll get an extra point there. Let's move on to the next question. Alright, question 4. So we have f being a function defined on -3.4, with f of 0 is 3. We have f prime of x given below with a line segment and a semicircle. So part A asks, in what intervals, if any, is f increasing? Okay, so with these kind of questions, where you can see they're like asking us stuff in words, and it seems like this is about increasing, this is about point of inflection. None of those are about f prime of x. What you want to do here, your main strategy, is going to be taking what they give you in your question and converting it into information about f prime of x, because that's what we have information about. So we'll take what they give us, f is increasing, and then ask ourselves, what does that tell us about f prime? Look at what they tell you in the question. What does that tell us about f prime of x? That's the key to this kind of questions. So f is increasing. That tells us that f prime of x is positive. That's the thinking that they want you to have when they're approaching these kind of questions. F is increasing, so f prime of x is positive. Now we can look at our graph of f prime, figure out where it's positive, and we're done, right? Easy as. So it's pretty clear that f prime of x is positive from -3 to -2, right? It's positive here, and then for the whole rest of the time it's negative. So f prime of x is positive from -3 to -2. So we'll say, okay, well, f is increasing from -3 to -2 because that was when f prime of x is positive. That was a 2-point question, one for the answer, one for the explanation. Alright, part 2. Find the x-coordinate of each point of inflection on the graph of f from -3 to 4. Why? Okay, so we're going to solve this kind of problem the exact same way as we did for the first part. Look at what they give us, and how does it relate to f prime of x? So we know that we were looking at points of inflection. Right? Point of inflection. If there's a point of inflection, what does that tell us about f? Well, it tells us that, first of all, we know that f prime of x is 0, right? That's when there's a point of inflection. And we also know that f prime of x switches direction. That's the key to solving this question. F prime of x switches direction at points of inflection. Okay? So now we'll just go here and identify all times where it switches direction. And make sure, we're talking about switching direction, not switching sign. So we're saying like when it goes from decreasing to increasing or increasing to decreasing. So let's go and take a look at f prime and see where it switches direction. So here it's heading down, 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 down. Now it switches to up. So that's somewhere where it switched direction. Up, 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 down, 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 down. So here's another place where it switched direction. So we went from down to up to down. So these are the two places where we switched to direction, right? So that means that these are the two places where f prime of x switched direction. Those are the two places where we have points of inflection. Okay? So we can say, well, since f prime of x switches direction, x equals 0 and x equals 2, we have points of inflection there. That will be justification. So we get 1 point for correctly identifying the 2 points, and another point for the answer. Alright, so in part C, find an equation for the line tangent to the graph of f at the point 0, 3. Okay, so when you're writing an equation for a tangent line, always, 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 you have to write down 2 things. Point and slope. You have to find a point, and you have to find the slope at that point, and then you're good. Okay, so they've been really nice. They gave us the point, 0, 3. What we need to do is find the slope at that point now, right? And remember, the slope of f, that's f prime. So we want to find f prime of x when we're at 0, 3, right? So at x equals 0, what is the derivative? The way we can figure that out is by looking at our graph, and we notice that when x equals 0, f prime is -2. So since f prime is the slope at any point, f prime of x at x equals 0 is the slope of f at x equals 0. So the slope is -2, since f prime of 0 is -2. Okay, so now that we have the point and the slope, we can put this into point-slope form. Y minus 3 equals -2 x minus 0. Boom. Done. Finished. That's 1 point right there. Let's move on. Okay, part D. Find f of -3 and f of 4. Show your work. This question is actually kind of deceptively tricky. It's harder than it looks. So before we get started, I want to quickly remind you of the fundamental theorem of calculus, FTC. So what the fundamental theorem of calculus says is if we're integrating from a to b, f prime of x, that's equal to f of b minus f of a. Okay, we're going to use that a lot in this part of the problem, so make sure to keep that in mind. Make sure you have a good grasp of that. So to find f of -3, okay, what we're going to do is we're going to use -3, and we're going to use one other point and plug those into a and b. Okay, so the question is, what is the point that we know the most about on this function? The point we know the most about is 0, 3, right? Because we've been working with 0, 3, and we know that at x equals 0, f of 0 is 3. So we know that f of 0 is 3. So we're going to use the fact that f of 0 is 3, and we're going to combine that with the knowledge of the fundamental theorem of calculus to help this problem, okay? So for f of -3, what I'm going to do is I'm going to go from -3 to 0 of f prime of x. The x why are you doing that? Why are you doing that? Well, I'll tell you. So this, by the fundamental theorem of calculus, is equal to f of 0 minus f of 3, right? Or f of -3, right? Well, hang on. Let's think about this. We can figure out f of 0, right? We know it's equal to 3. And we can figure out this integral. That's just 0. That's just, we have to take some areas with triangles and stuff there. We can figure this out. We can figure this out. So that'll allow us to solve for f of -3, right? The reason we used 0 here and not 1, for example, is because we know what the value of f of 0 is. If we chose 1, we wouldn't know what f of 1 is, so we couldn't be able to solve that. Okay, so let's solve this for f of 3 real quick. F of -3. This is f of 0 minus the integral from -3 to 0 of f prime of x, right? So let's solve this integral here. The area from -3 to 0, from here all the way to there. So what that's going to be is this triangle minus that triangle, because this is positive and that's negative, right? And something I noticed right away is that this triangle and this small triangle here, they cancel out. So I'm just going to ignore those two and just focus on this leftover region in blue here. Right? If I just find the area that's blue region, that's going to be the same thing. So since each square is 1, this square is 1, this square is 1/2, and since we're negative, the total is going to be -3/2, right? So this integral is -3/2. Okay, and we know f of 0 is 3, right? So they gets us that f of -3 is 3 minus -3/2. Don't bother simplifying that. Okay, so if you didn't get that, try solving for f of 4, because the technique is very similar. If you didn't get that, try f of 4, and then we'll see how we do it. Okay, so f of 4 is the exact same thing. What we're going to do is we're going to take the integral from 0 to 4 of f prime of x dx and say that's equal to f of 4 minus f of 0. We can figure out f of 0. We can figure out this integral, and that allows us to figure out f of 4. So if I solve for f of 4, I'll get f of 4 is 0 plus the integral. So now all we have to do is figure out the area from 0 to 4. So that's going to be, if I shade it in purple, it's going to be this region and this region. Border. Yeah, there goes so that region. Okay, so we'll figure that out. So we'll say, okay, this entire rectangle has a height of 2 and a length of 4. So this entire rectangle, I'm just dealing with magnitudes here. Let's not use white. I'm just dealing with magnitudes here. This entire rectangle has 8. And then I'll subtract the area of the semicircle. So the area of the semicircle is 1/2 times pi times the radius squared. And the radius is clearly 2, so it's 4, which is 2 pi. Right? So the area of the semicircle is 2 pi, and then that means the area of the purple is 8 minus 2 pi. 8 minus 2 pi. And then since it is a negative region, I'll just put a negative sign in front, since it's under the x-axis. Also, I realized I made a typo here. I said 0 here. It should actually be, I don't know if I can squeeze it in there, f of 0. Okay, so anyways, we have f of 4 equals 3 plus negative of 8 minus 2 pi. Okay, and that's that. So this is a 3-point question. 1 point coming from finding the area of this net region in the triangles. Another point for getting f of -3. 1 point for figuring out this area of the semicircle, of the missing semicircle area. And then a 4th point for the correct answer for f of 4. Okay, so for this question we have a coffee pot in the shape of a cylinder with radius 5 inches, and we have h being the depth of the coffee in the pot. So h is not a constant, h is changing based on how much coffee there is. Where h is a function of time t, the volume V is changing at the rate of -5 pi square root of h. And then we have the formulas for the volume of a cylinder. Okay, so in part A, we need to show that dH dt is negative square root of h over 5. Okay, so first of all, we know that the volume is pi r squared h, right? And then since r is always 5, we can plug in 5 for r, and that'll get us 25 pi h. Okay, so if I were to take the derivative of both sides to solve for dv dt, I'd get that dv dt is 25 pi h dt, right? And the reason I did that is because I also know that the volume is changing at a rate of -5 pi square root of h, right? So I know that this is dv dt, and I know that this is dv dt, so that'll allow me to set this equal to each other. So I know that this is equal to -5 pi square root of h. Right, this relation, I'm not gonna put this outline. This relationship will allow us to simply solve for dH dt. Okay, so let's see, we can cancel the pi's. We can divide by 25. So let's white. dH dt is -5 over 25 is 1 over 5 square root of h. So dH dt is equal to negative square root of h over 5, right? Isn't that what they showed us in the beginning? Yeah, dH dt is negative square root of h over 5. So, ta-da, we've shown it. We're done. Okay, so let's see. So in terms of points, this is a 3-point question. 1 point for taking the derivative of the volume equation. Another point for recognizing the similarity between that and the equation they gave us in the problem. And then so the 3rd point would come from doing all the stuff and solving for dH dt. So given that h equals 17 at time t equals 0, solve the differential equation as a function of t. Okay. dh dt is negative square root of h over 5. Solve this for h as a function of t, okay? So the first step is going to be separating our variables. In this case, we only have one variable, but we're going to separate it anyways because we want to. So let's bring the h's onto the left side. So we'll have 1 over square root of h dh equals negative 1/5 dt. Now that we have our h's on one side and our everything else on the other side, we can integrate both sides. Okay? Let's do this in a separate little region. So the integral of 1 over square root of h dh. If we want to rewrite this in terms of an exponent, that would be, well, this is h to the 1/2, but since it's in the denominator, we're going to flip it and make that negative. So h to the negative 1/2 dh. And if we were to integrate that, we would get 2 h to the 1/2, or 2 square root of h, right? Since we are adding 1 and multiplying by the reciprocal. So that gives us 2 square root of h equals, if we integrate this, that's negative t over 5. Now we're going to plus c. Okay, so now's the good time to apply our initial condition. So if t equals 0 and h equals 17, we can plug in t equals 0 and h equals 17, and we'll get 2 times the square root of 17 equals, well, this is just going to become 0, right? Plus c. So c is equal to 2 square root of 17. And we can plug that into here. We can say 2 square root of h equals negative t over 5 plus 2 square root of 17. And then if we wanted to solve this for h, we'll divide everything by 2 first of all, and then square it. So h is negative t over 5 plus 2 square root of 17. First we divide that whole thing by 2, right? And we take that entire thing and we square it, because it's a square root here. And that is solved for h. Okay, so points. This was a big one. First point came from separating the variables. Second point came from correctly integrating the 1 over square root of h. The third point came from correctly integrating the negative 1/5. The fourth point came from using the initial condition. And the fifth point came from correctly solving for h. Finally, part C. At what time is the coffee pot empty? Okay, so now we have to use a tiny bit of logic. So if the coffee pot is empty, the height is going to be 0, right? So h equals 0. And give me a minute, I'm just going to rewrite the equation that we got in part B. Alright, did that. So we know that this is the expression for height and time. So if we want to figure out the time where h is equal to 0, I can just replace this h with 0 and solve this for t, right? So we'll get that the whole negative t over 5 plus all this fun stuff squared equals 0, right? So let's see, I'll take the square root of both sides and multiply by 2 to get rid of those extra things. So that'll give me negative t over 5 plus 2 square root of 17 equals 0. I'll subtract negative 2, I'll subtract 2 square root of 17 to get me negative t over 5 is negative 2 square root of 17. I can cancel the negative signs, multiply by 5, and that'll get me t is 10 square root 17, like that. Look at that, awesome. So that is part C. That was the last one. That was a pretty nice, calm part C. That was a 1-point question. We're done with that. Move on to question number 6. Okay, question 6, the final question for the 2003 AB exam video. So we have the function f as this piecewise function, square root of x plus 1 for x between 0 and 3, and then 5 minus x for x between 3 and 5. So part A asks, is f continuous at x equals 3? Explain why or why not. So this goes all the way back to like the first week of calculus. where we're talking about continuity of functions and limits and stuff like that. So to recap, if a function is continuous at a value, we need three things to be true. First, so since we're dealing with x equals 3, we need f of 3 to exist. That's condition number 1. Condition number 2 is that the limit as x approaches 3 of f of x also exists. So we have f of 3 exists and the limit exists. And then the third condition for continuity is that f of 3 has to equal the limit as x approaches 3 of f of x. So once all three of these conditions are met, then we can determine that the function is continuous. So let's go and do that one by one, okay? So f of 3. F of 3, the way we can figure that out is we'll just take 3 and plug it into this function. So if we see here, we have for 0 is less than or equal to x is less than or equal to 3. That means we need to look at this top part of the function when we're dealing with 3. Because here it's only if x is greater than 3, not greater than or equal to. So we're going to plug it into this top part. So f of 3 is the square root of 3 plus 1, which is the square root of 4, which is 2. Okay, so f of 3 exists and it is 2. So it doesn't have to be a certain value, it just has to exist. So we're good there, right? Now let's move on to the second thing. The limit as x approaches 3 of f of x has to exist. So for the second condition, what we have to do is we have to look at the limit from the left and from the right, okay? So if we look at the limit as x approaches 3 from the left, that's going to be what happens if you plug in 3 into this one. And we already determined that it's 2, right? So as x approaches 3 from this left part, it approaches 2. And then we also need to look at the limit as x approaches 3 from the right of f of x. So that's looking at this part. So if we plug in 3 into that part, it's going to be 5 minus 3 equals 2. Basically what we're doing is we're checking that if we were drawing a graph or whatever, the function doesn't like make a jump, right? This would be a non-continuous function because it's approaching one thing from this side and it's approaching something else from the other side. So we want to make sure that the function is smooth, right? It's approaching the same thing from the left side as it is from the right side. Okay, so now we've determined that since these are both the same number, the limit exists. So we can say that the limit as x approaches 3 of f of x equals 2, right? Same thing from the left and the right. So that condition is met. And then what's the third condition? F of 3 is equal to the, well, what's f of 3? F of 3 is 2. What's the limit? The limit is also 2. Since f of 3 is equal to the limit as x approaches 3 of f of x, these two are both equal, the third condition is met. So we've met all three of our conditions, so that means we can say that f is continuous at x equals 3. And if we want to explain why or why not, we'd say, well, yes, because the limit from both sides is equal, so the limit exists, and that limit equals the value of f of 3. Okay, so this was a 2-point question, 1 point for the right answer, and 1 point for the explanation. Okay, so part B, we need to find the average value of f of x on the closed interval from 0 to 5. Let's quickly remind ourselves of what the average value function is. So if we want to find the average between a and b, I'll write like a and b, the way we do that is we do 1 over b minus a times the definite integral from a to b of f of x. Okay, so this is the formula to find the average value of the function between 2 points a and b. In our case, a is 0 and b is 5. Okay, and then we can put that into here. So that means we want to figure out the integral from 0 to 5 of f of x dx. And we have a little bit of a problem here, because if we're going from 0 to 5, we have two different functions. One of them is for between 0 and 3, and the other one is between 3 and 5. So which one do we plug in? Do we plug in this one? Do we plug in this one? Do we plug in both? Do we take the average of the two? What do we do? So the way we're going to approach this is we're going to split this up. We know that this is equal to, we can take it as the limit from 0 to 3 of f of x, and then we can add the integral from 3 to 5, right? It's kind of like we have this entire area from 0 to 5, and we're splitting it into the first section, that's from 0 to 3, and then the second section from 3 to 5. So we'll find this integral separately, we'll find this integral separately, and we'll add these two together to get our answer. We're taking this integral from 0 to 5, and we're splitting it up into two integrals. Sorry, one sec. Okay, so we split it up into two different integrals, and then now the nice thing is this, for this left integral, we know to use this top function, and for this right integral, we know how to use the bottom function. So let me erase this, and we can solve these two integrals, right? Okay, so for the first one, we'll be integrating from 0 to 3 of the square root of x plus 1 dx. Okay, so this is going to be, if we want, we can do a u substitution, but since the coefficient for the x term is 1, you don't really have to do a u substitution. So if we do this, we can just treat this like one thing. Again, if there was like a 2 here for a coefficient, then you'd have to do a u substitution. But since there's no coefficient for the x, we can just pretend like it's just an x. So they'll get us. So this is. Let me rewrite this as. Let me rewrite the square root as a 1/2 power, because when you're dealing with integrals and messing with the exponents, it's nice to have it in that form, in the fractional form. So we add 1 to this and multiply by the reciprocal. So that's x plus 1 to the 3 halves, right? Because 1/2 plus 1 is 3 halves. And we multiply by the reciprocal, so times 2/3, right? And remember, we're still going from 0 to 3. Okay, so now we need to plug in some numbers here. So this is equal to, so we plug in 3 here, we'll get 4 to the 3 halves times 2/3 minus, plug in 0 here, we'll get 0 plus 1 is 1. So 1 to the 3 halves times 2/3. Okay, and I don't really want to simplify this, so I'll just leave it as is. That's going to be I'll bubble this in, I guess. That's going to be our part 1 of our answer, right? That's this integral. Now we'll move over to, let's do pink. For a second integral, we'll do pink. So it's the integral from 3 to 5 of the other part of f of x, right? So now we're dealing with this 5 minus x, because we're going from 3 to 5. So we're integrating from 3 to 5 of 5 minus x dx. This is a bit easier. It's 5x minus x squared over 2. Remember, we're increasing 1 to the power and dividing by that power. And we're going from 3 to 5. So this would be 5 times 5 is 25 minus, that's a really ugly 2. Okay, so 25 minus 5 squared over 2. That's for, we plug in 5. And if we plug in 3, we'll get 15 minus 9 halves, like that. Right? I'm just simplifying whatever I feel like. It's really, up to you. So, now we can put that together to find this integral, right? So, that means that the actual integral from 0 to 5 of f of x dx is going to be, so it's going to be what we get when we add up the blue part and the pink part, right? So I'm going to save you the time of watching me rewrite all of this, and we'll just skip to it. Okay, cool. So I went ahead and rewrote everything that we just did. So we found the integral, but be careful, we're not completely done yet. So if we go up and look at the question, it didn't ask us to find the value of the integral, it asked us to find the average value, right? So if we look over at our definition of the average value that we came up with, or that we've remembered from our class, we take the integral, we're multiplying it by 1 over b minus a, right? Since a is 0 and b is 5, this is going to be 1 over 5. So if I want to find the average value, I'll have to multiply it by 1/5. So I need to divide everything here by 5. And this gives us the average value of our function. Did they ask us for anything else, or is that it? Let's see. Yeah, they just found the average value. So this was a 4-point question. 1 point for splitting the integral up into 2 pieces. 1 point for evaluating the blue integral. 1 point for evaluating the pink integral. And 1 point for the final answer. Alright, so part C, we have the function g. So we're dealing with another function. We're not dealing with f anymore. So the function g is defined by this. So this looks very similar to f. They're both piecewise. They both look very similar. One part is going from 0 to 3. Other part's going from 3 to 5. And then, but the main difference that's pretty obvious is we have these k and m things here. These are other constants, it seems. So let's read through the problem. The function g is defined by this. K and m are constants. If g is differentiable when x equals 3, what are the values of k and of m? Okay, so the big part that you need to think about when you read this problem is this one key word here. Differentiable. That's the key to this entire problem. Differentiable. So what does differentiable mean? Well, it means that the derivative from both sides is equal at x equals 3. So you have your function, and then the slope is approaching the same number from both sides at x equals 3. So you can take the derivative there. Okay? And then the other big thing to realize is that if a function is differentiable at a point, it's also continuous at that point. So differentiable implies continuity. Okay? This is the key relationship that they want you to know to help you solve this problem. Okay, so what does it mean if the function is continuous at x equals 3? Well, if I have these two, if I plug in 3 into this part and 3 into this part, they should both equal the same thing, because at x equals 3, the function is continuous, right? So this is what I'd get if I approached 3 from the left. This is what I got when I approached 3 from the right. Since the function is continuous, these both are the same at x equals 3. So I can plug in 3 and I'll get k times the square root of 3 plus 1 is 4 is equal to m times 3, so 3m plus 2. Okay? I'm just going to leave that off to the side. And we also know it's differentiable. So what does that tell us? Well, if we take the derivative of this and the derivative of this, and we plug in x equals 3, since the derivatives are also the same on the left and the right, we can take the derivative and plug in 3, and we should still get the same number. So let's take the derivative of both of these parts of the piecewise function. We'll start with the top one, k times the square root of x plus 1. And remember, k is just a constant. K is not another variable. So if we take this derivative, since there's no coefficient here next to the x, we can just treat this kind of like a square root of x. And this is going to give us k over 2 square root of x plus 1. Okay? If you wanted to use the chain rule, I guess, since this is a composite function, you'd multiply by the derivative of x plus 1, which is 1. And then now we can take the derivative of the second part of the function. So the derivative, what's the second part of the function? Mx plus 2, right? Mx plus 2. Remember, m is just a constant here as well, just like k was. So if we take the derivative of this, we're just going to get m. Okay? And remember, the function is differentiable, so when I plug in x equals 3, this equals that. Alright? So that gives us our second equation that we can use. That equation being k over 2 times the square root of 3 plus 1 is 4 equals m. Okay, so now we have two equations, two variables, k and m. So these will allow us to solve for our two variables. Okay, let's see how we can do this. I'll simplify this a bit. Since the square root of 4 is 2, 2 times 2 is 4. This says that k is equal to 4m, right? And then this says that 2k is equal to 3m plus 2. So these are the simplified equations that we're going to use, right? What I'll do now is I will take this and plug it in for this k here. So that'll get us 2 times 4m, right, replacing this k with the 4m, equals 3m plus 2. 8m equals 3m plus 2. 5m equals 2. M equals 2 over 5. Okay, but they asked us for both m and k, so it's an easy enough thing to figure out k. So I can take this relationship between k and m, and I'll say, okay, well, since k is equal to 4m, k is equal to 4 times, well, m is 2 over 5, so I can do that. So k is equal to 8 over 5. Okay, so we found the value of k and m by using the fact that if the function is differentiable, then it is also continuous. Okay, so this was a 3-point question. The first would come from finding one of these equations. The second would come from finding the other equation, and the third would come from finding the actual values of m and k. All right, so that was it for this review video, or for this explanation video of the 2003 AP AB Calculus exam. If you found this helpful, and I will see you in the next video. Goodbye.